For the calculation of oxidation state of the atoms in a molecule, various empirical rules have been framed. Based on those rules, we have to calculate the oxidation number of each and every atom present in the molecule. So first let us discuss about the first rule. First rule explains the oxidation state of the hydrogen atom in various molecules. Usually, if hydrogen is present in any molecule, based on the nature of the molecule, either we will assign a -1 or 0 or +1 oxidation state to the hydrogen atom. Because in every bond formation, hydrogen atom either it can lose 1 electron or it can gain 1 electron, or if it participates in the covalent bond formation, it will share only 1 electron. Hence, we will assign 3 values, -1, 0 or +1. For example, if hydrogen participates in the homoatomic molecule like H2, here oxidation state of the hydrogen is 0. Next, if hydrogen exists along with the first group metals or second group metals, that means like lithium hydride, sodium hydride, potassium hydride, like that. In these elements, for hydrogen, we will give the oxidation state -1. Similarly, in case of the hydrides of the second group metals like calcium hydride and magnesium hydride, barium hydride, in these compounds we will assign the value -1 for hydrogen. Next, in all the other covalent molecules like in H2O, in HCl, next in CH4, the oxidation state of the hydrogen is +1. So for hydrogen we will give 3 values, -1, 0, +1. This is the first rule about the oxidation state calculations. Next, second empirical rule. It explains the oxidation state of the oxygen. So how to calculate the oxidation state of the oxygen? Similarly, if oxygen is in a homoatomic molecule, the oxidation state of the oxygen is assigned 0 value. Next, if oxygen exists along with the fluorine like in O2F or O2F2, here for oxygen, we will give the positive oxidation state, that is +1 or +2. +1 or +2. Next, if oxygen is present in any peroxide like in H2O2, Na2O2, here in all these molecules, we will assign the value -1. Next, in rest of the compounds, usually we will give the oxidation state for oxygen -2. So, therefore, in the normally when we come across with various compounds, we will find 3 oxidation state values for the oxygen, either 0 or +1 or +2, -1 or -2. But in very few compounds like in what is called superoxides, KO2, here the oxidation state of the oxygen is -1/2. These are the different values that we can assign for oxygen. Next, the oxidation state of the third rule, it says about the fluorine, the oxidation state of the fluorine. When fluorine is in homoatomic molecule, the oxidation state of the fluorine is 0. If fluorine is present in any heteroatomic molecule like in HF or say for example in OF2 or in some other molecule like say NaF, in all the heteroatomic molecules for fluorine we will give the value -1. Next, the oxidation state of the first group metals, that means first group and second group metals. For first group metals like lithium, sodium, potassium, rubidium, cesium, we will assign the value +1. Next, for second group metals like beryllium, magnesium, calcium, strontium, barium, we will assign the value +2. Next rule, if the given ion is a monoatomic ion like sodium ion, like chloride ion, in case of monoatomic ions, the charge shown over the ion itself is taken as the oxidation state. Similarly, in case of the multiatomic ions like SO4 2-, next ClO4-, next in MnO4-. In case of multiatomic ions, the sum of the oxidation states of all atoms is equal to charge shown over it. For example, here sulfur, we don't know the oxidation state of the sulfur. Let us say put X. Next, for calculation of oxidation state of the oxygen, we have to cross check the given formula with the formula of the peroxide. If it coincides with the formula of the peroxide, then you assign -1 for oxygen. Again, you cross-check this given compound with the normal oxides. If it coincides with the normal oxides, then you can give the oxidation state -2 for oxygen. Like that, through cross-checking with the standard compounds like fluorocompounds, peroxides, superoxides, normal oxides, we have to assign the oxidation state of the oxygen. But usually, we will find the compounds of the oxygen as oxides. Therefore, usually we will give the -2 oxidation state for the oxygen. So, for one oxygen, if the oxidation state is -2, for 4 oxygens, what is the total oxidation state? So, -8. So, for sulfur, oxidation state is X. For 4 oxygens, -8. So, X plus -8 is equal to -2. Therefore, X is equal to +6. Like that, we can find out the oxidation state of the unknown atom by using this rule. The rule is sum of the oxidation states of all atoms present in a multi-atomic ion is equal to the charge shown over it. By using this rule, we can find out the oxidation state of the unknown atom. Similarly, for chlorine, we can find out. Say chlorine oxidation state is X. Next, for each oxygen, -2. So, therefore, -8 is equal to -1. Therefore, X is equal to +7. Similarly, for manganese, we want to calculate the oxidation state. Assign the value X. X plus -8 is equal to -1. Therefore, X is equal to +7. Like that, we can find out the oxidation states of the any unknown atom in any multi-atomic ion by using this rule. Next, in case of the organic molecules, if we want to find out the oxidation state of the any carbon atom, it is better to calculate the oxidation state by following the structure instead of following the empirical rules. Because we can't directly apply the empirical rules for the calculation of oxidation state of the carbon in the molecules. Therefore, if they say, for example, if they give the acetaldehyde, if they ask the oxidation state of the each and every carbon atom separately, we will calculate it through one method. If they ask the average oxidation state, we will calculate in a different way. So, for that purpose, for every organic molecule, while calculating the oxidation state of the carbon, first you represent the structure of the molecule. Based on the structure only, you try to find out the oxidation state. So, for example, if you know the structure like this, now we know carbon is more electronegative, hydrogen is less electronegative. While calculating the oxidation state based on electronegativity values, first you observe the number of bonds present between dissimilar atoms. If single bond is present, the more electronegative atom always gain 1 electron through that single bond. The less electronegative atom always loses 1 electron through that single bond. Therefore, here carbon is more electronegative. Therefore, around this carbon 3 bonds are present. Through this bond it will gain 1 electron. Through this bond it will gain 1 electron. Through this bond it will gain 1 electron. So, therefore, total carbon has gained 3 electrons. Next, here carbon. This carbon, see, through this bond, hydrogen is less electronegative, carbon is more electronegative. Therefore, carbon has gained 1 electron through this bond. So, therefore, through this bond, its oxidation state is -1. Next, similarly, this carbon and oxygen. Here, double bond is present. Oxygen is more electronegative. Since oxygen is more electronegative, oxygen will gain the 2 electrons through these 2 bonds. Therefore, carbon here loses 2 electrons. Therefore, the net charge present over the carbon here is +1. Next, for this carbon, see the oxidation state through these 3 bonds is -1. Through this bond is present between 2 identical atoms. Therefore, through this bond, this carbon atom neither loses nor gains the electrons. This carbon also neither loses nor gains the electrons. Therefore, for this carbon, oxidation state is -3. For this carbon, oxidation state is +1. So, if they ask the individual oxidation states, you can report the answer like this, -3 +1. But sometimes they will ask the average oxidation state. For calculation of the average oxidation state, directly you can apply the empirical formula like this, C2H4O. By applying this molecular formula, directly we can calculate the oxidation state. So, for example, according to those rules, say carbon, we don't know the oxidation state of the carbon, let us say X. Next, 2 carbons are present, 2X. Plus 4 hydrogens are present, so +4. Plus -2. Sum of the oxidation states in a neutral molecule is always equal to 0. Therefore, 2X is equal to +2 -4. Therefore, minus 2. So, x is equal to minus 2 by 2. So, minus 1. Minus 1. So, here also you see minus 3 plus 1. Minus 2 by 2, same answer. Based on these values also, the average oxidation state for carbon will become minus 1. Here also we got the same minus 1. So, for organic molecules, so either they can ask the average oxidation state or they can ask the individual oxidation states. Based on the way they ask, you have to report the answer according to the question. Next, similarly for peroxides, if you apply the rules directly for peroxides, again we don't get the correct answer. Therefore, when they give one particular molecule, you have to cross-check whether the given molecule is a peroxide or not. So, how to know whether it is a peroxide or not? For that purpose, already you should have the idea about which are peroxides and which are not peroxides. This is hydrogen peroxide, this is a lithium peroxide, this is a sodium peroxide, this is a potassium peroxide, rubidium peroxide, cesium peroxide. Next, here in the second vertical column, beryllium, magnesium, magnesium peroxide, calcium peroxide, strontium peroxide, barium peroxide. So, these are the total peroxides that are existing in the chemistry. So, these are the elements which can produce the peroxides. So, if you have the rest of the elements, that means elements of the D block, elements of the P block, they never produce the peroxides. If you have the idea about the peroxides, then only you can predict the oxidation state of the oxygen in the given compound. So, therefore, for peroxides also don't apply the rules directly. If you remember the formulas of all peroxides, soon after observing the given compound, after identifying the given compound, then you can find out the oxidation state. Next, oxidation state of the sulfur compounds. See, in all sulfur compounds, again, for certain sulfur compounds only we can apply the rules. For majority of the sulfur compounds, again, the rules are not applicable. For example, the given compound is a H2SO5. If you apply the rules, we will get one particular value. Let us say, for example, if you apply the rules, oxidation state of the 2 hydrogen atoms is +2 and sulfur is X. Oxidation state of the 5 oxygen atoms is -2. Therefore, if we calculate the sum of the oxidation states is equal to 0. Therefore, X is equal to +10 -2. That means +8. So, we will get the +4. But the actual answer is wrong. Therefore, for sulfur compounds also, don't apply the rules directly. In order to calculate the oxidation state of the sulfur in any sulfur compound, it is better to know the structure. By following the structure, you always try to calculate the oxidation state. So, for H2SO5, this is the structure. See, in H2SO5, here one peroxy linkage is present. So, wherever peroxy linkage is present, you assign the oxidation state for each oxygen present in the peroxide -1. So, this is -2, this is -2, this is -2, this is -1, -1. Now, for sulfur, you see here through this bond, sulfur has lost 1 electron. Through this bond, it has lost 1 electron. Through these 2 bonds, it has lost 2 electrons. These two bonds, it has lost 2 electrons. Total oxidation state is +6. So, therefore, if you know the structure, then only we will get the correct oxidation state for the sulfur. Not only for H2SO5, the another molecule is H2S2O8. Here again, if you follow the structure, you will get the correct oxidation state of the sulfur. See, here also one peroxy linkage is present. Because of the presence of the peroxy linkage, so if you apply the rules directly, we will get some wrong results. Therefore, here oxidation state of the sulfur is +6, +6. Similarly, for H2S2O7. Here oxidation state is again +6. +6. Next, calculation of the oxidation state of the central atom present in the inorganic complex molecules. Say, for example, this is one complex molecule. So, now we want to find out the oxidation state of the iron atom present inside the complex ion. So, in order to apply the rules for this complex ions, it is better to have the little knowledge about these ligands. Inside the complex, whenever if you find H2O, if you find CO, if you find NO, this NO, next NH3. These ligands are usually considered as the neutral ligands. Therefore, the charge carried by each molecule of H2O, CO, NO, NH3 is 0. Therefore, these are neutral ligands, their oxidation state is 0. For rest of them, always assign negative charge for each ligand based on the nature. Next, in case of the complex molecules, see if particular unit is shown inside the square brackets, either before the unit or after the square bracket unit, they will show certain ions. Those ions are called counter ions or simple ions. If the simple ions are shown before the complex ion, you assign positive charge for them. Then automatically the complex will get the negative charge. Whereas in certain complexes like this CrNH3, 6 times here. For these molecules, see in this molecule, see the simple ion is shown after the complex. So if any simple ion is shown after the complex, they will get the negative charge. Now the complex will get the positive charge. Positive charge. So therefore, based on the relative position of the simple ions, you identify the charge of those simple ions. Charge of those simple ions. Next, based on the nature and number, first you identify the total charge carried by the simple ions. Here 3 chlorides are shown, so therefore total charge of the chlorides is minus 3. If the chlorides charge is minus 3, the complex will get the charge plus 3. Similarly here, simple ions, the total positive charge is plus 4. Here the oxidation state of this complex ion is minus 4. Like that, based on the relative position of the simple ions, first identify the charge carried by the complex. Based on the number of the simple ions, identify the charge carried by the complex ion. Then after getting the idea about the charge of the complex ion, now we can find out the charge carried by this metal atom. So let us say we want to find out the oxidation state of the chromium here. So let us say X. Similarly, we want to find out the oxidation state of the iron here. Let us say X. Next, cyanide ion. Cyanide ion, wherever they are present, each ion will carry 1 unit negative charge. Therefore, 6 such ions are present. So, minus 6 is equal to minus 4. Therefore, X is equal to minus 4 plus 6. So, therefore, here plus 2. Similarly, X. Ammonia. Each ammonia oxidation state 0, neutral ligand. X plus 0 is equal to plus 3. Therefore, X is equal to plus 3. So, like that, for complex molecules, apply the principles in this manner. Next, oxidation state of the chromium in chromium peroxide. Here in chromium peroxide, so this is one peroxy linkage, this is one peroxy linkage. The oxygen atom involved in the peroxy linkage will always get the 1 unit negative charge. Here oxidation state minus 2. Therefore, total oxidation state of the chromium is plus 6. Chromium is plus 6. Therefore, so if you apply the structure, then only you will get the plus 6. Directly if you apply the empirical rules, you will get a different value. Next, these oxidation state calculations we are doing according to one empirical principles. The oxidation state that we get through these calculations does not represent the actual charge carried by the atoms. The actual charge carried by the atoms can be calculated through formal charge principle. Therefore, formal charge of atom. Formal charge of the atom is equal to, if we calculate the formal charge of the atom through this principle, the result what we get through this principle will directly represent the charge carried by the atom. So, formal charge is equal to number of electrons in valence shell of isolated atom minus number of electrons contributed for bond formation. Number of electrons contributed for bond formation minus number of free electrons left. Through this formula, if we calculate the charge, that is the actual charge carried by the particular atom in a given molecule. Let us say, for example, First, let us apply for this principle for the calculation of the formal charge of oxygen present in O2 molecule. So, this is the O2 molecule. Next, here one lone pair, another lone pair. Here one lone pair, here another lone. That means at each oxygen, 2 lone pair of electrons are present. Number of electrons in valence shell of the isolated atom, 6. Next, minus number of electrons contributed for bond formation, 2 electrons. Next, number of free electrons left, 4. So, therefore, charge left over the oxygen is 0. So, this is the actual charge carried by the each oxygen atom in O2 molecule. Similarly, let us calculate the formal charge of the each oxygen in the ozone molecule. Here, 2 lone pair of electrons are present. Here, 1 lone pair of electrons have been donated to this oxygen. So, here only 1 lone pair is left. Here, originally 2 lone pair of electrons were there. Now, after receiving 1 lone pair, it becomes 3rd lone pair. Now, let us say I label this oxygen as 1, 2 and 3. Now, let us calculate the formal charge of the each and every oxygen atom separately. First, I am calculating the formal charge of this first oxygen. Formal charge of the first oxygen. First oxygen. So, number of electrons present in the valence atom. Sorry, number of electrons present in the valence shell of isolated atom. Next, minus number of electrons contributed for bond formation. For bond formation, 2 electrons. Next, number of free electrons left. Therefore, formal charge here is 0. Next, formal charge over the second oxygen. Formal charge of second oxygen. Number of electrons in the valence shell. Next, number of electrons contributed for bond formation. Here 1, here 1, here 1. Next 1. Next here 2 electrons. So, therefore, formal charge is 1. Formal charge is 1. Next, formal charge of the third oxygen. So, electrons in the free atom. Next, total number of electrons contributed for bond formation. Next, 6 electrons. So, -1.